Probably one of the most compelling images in the history of mankind is Rutherford's planetary model of the atom. In this model, the nucleus was likened to the Sun and the electrons to the planets that orbited it. Like it or not, this is the image that comes to mind whenever we think of an atom, a tiny solar system, orderly and complete. Unfortunately, this beautiful picture did not survive scientific scrutiny. The problem with the planetary model lay not in the nucleus, but in the electrons that circled it. During this epoch, the newly discovered electron was at the center of intense scientific attention. It had been proved, time and again, by multiple scientists, that an electron in motion inevitably radiates energy in the form of electromagnetic waves. This principle, established by Joseph Larmor, was one of the cornerstones of classical electrodynamics. And therein lay the paradox. In Rutherford's atom, each electron is in constant acceleration, endlessly turning about the nucleus. By Larmor's law, it should therefore be continuously radiating energy, losing momentum with every turn. Within a fraction of a second, it should spiral inward and crash into the nucleus. If the laws of electromagnetism were correct, then the atom, and all matter built upon it, could not exist. This was not a small flaw but a fatal one. Rutherford had given the atom form, but not stability. The model explained the scattering of alpha particles, but not the endurance of matter itself. The planetary atom was beautiful and impossible. Bohr and the empirical rescue of the atom. Niels Bohr was no stranger to Rutherford's planetary model. Having worked with Rutherford himself, he knew its strengths and its fatal weakness. An orbiting electron, being a charged particle in constant acceleration, should radiate energy and fall into the nucleus. Yet atoms were clearly stable. Bohr's response, in 1913, was revolutionary. He proposed that electrons could occupy only certain discrete orbits, stationary states, where, by some new law of nature, they did not radiate energy at all. When an electron shifted from one of these states to another, it emitted or absorbed light in precise quanta. What made Bohr's idea compelling was its empirical proof. The wavelengths of the hydrogen spectrum, first described by Johann Balmer, fit his formula exactly. The spectral lines were no longer mysterious patterns, they were the visible signature of electrons leaping between allowed orbits. For the first time, the atom's inner workings seemed to match experiment with mathematical precision. The Bohr model was a triumph, but a fragile one. It declared stability without explaining it, and introduced quantum jumps that defied continuity and common sense. Nevertheless, it succeeded spectacularly where Rutherford's model had failed. It predicted the data. The colors of hydrogen's light were now the fingerprint of the atom's internal structure. Yet the deeper question remained unanswered. How did the electron know when to jump, and why did it not radiate in between? There was no answer. Bohr had given the atom a language that matched observation, but not understanding. It was an elegant compromise between physics and mystery. From Bohr to de Broglie, the bridge between particle and wave. Bohr's atom had triumphed by matching theory with the hydrogen spectrum, yet it remained a structure of rules, not causes. It could predict the color of light emitted by hydrogen, but it could not explain why those orbits existed, or what governed the mysterious quantum jumps. In 1924, a young French physicist named Louis de Broglie proposed an audacious idea that changed everything. If light, once thought to be a wave, could behave as a particle, then perhaps matter, long treated as particle, might also behave as a wave. Every moving particle, he argued, should be associated with a wavelength inversely proportional to its momentum, a matter wave. De Broglie's vision transformed Bohr's arbitrary orbits into something physical. The only stable paths were those in which the electron's wave fit exactly around the nucleus, closing on itself like a vibrating loop. The atom's quantized energy levels now reflected whole numbers of wavelengths, not mystical permissions. It was a profound synthesis, the planetary atom reborn as a wave system. And it laid the foundation for Erwin Schrödinger, who soon gave de Broglie's concept mathematical form. The hidden dimensions of Schrödinger's equation. Schrödinger's wave equation brought a new elegance to the atom. By describing the electron as a wave whose resonant patterns defined energy levels, it seemed to solve the riddle that had defeated both Rutherford and Bohr. Quantization now appeared to arise naturally, not as an arbitrary rule, but as a property of standing waves bound within the atom. But buried within this elegance was a fatal flaw, one that few dared to acknowledge. The wave equation worked perfectly for hydrogen, the simplest atom, with a single electron moving in 3 spatial dimensions. Yet the moment physicists tried to extend the equation to atoms with more electrons, the mathematics revealed its hidden cost. Each additional electron introduced its own set of spatial coordinates, 3 more dimensions for its position in space. The helium atom, with 2 electrons, required 6 spatial dimensions. Lithium, with 3 electrons, required 9 spatial dimensions. Carbon, with 6 electrons, demanded 18 spatial dimensions. By the time one reached oxygen, the mathematics occupied a space of 24 spatial dimensions. What had begun as a description of real motion in a 3-dimensional universe had turned into an abstraction of staggering complexity. The Schrödinger equation no longer described physical space, it described a configuration space, an imaginary mathematical construct where each electron had its own coordinate system. Physicists called this higher-dimensional realm Hilbert space, and they assured themselves that it was merely a convenient way to organize probabilities. But this was not a small step, it was a fundamental departure from physical reality. The atom, once a mechanical system in space, had become an equation in an invisible domain of infinite dimensions. The wave function that described it could never be visualized or directly measured, it existed only as a mathematical probability amplitude. In truth, Schrödinger's equation had not explained the atom, it had escaped it. Instead of describing what electrons were doing in real space, it described what could be said about them in an abstract mathematical space. The model's success in predicting spectra concealed the fact that it had abandoned any physical interpretation of the electron itself. This was the price of retaining quantization without mechanism, the loss of reality itself. By the mid-1930s, this was considered progress. But to a physicist seeking understanding rather than calculation, it marked the end of explanation. Stability of the atom, continuous virtual interaction. Classical physicists theorized that for the electron, a charged particle, to stay in a stable state as it orbited the nucleus in an accelerated state, would have to constantly emit radiation. The only problem was that if the electron radiated energy as it traveled around the nucleus, it would lose that energy and spiral into the nucleus in about 10 trillionths of a second. Augmented Newtonian Dynamics, and theory agrees with this estimation and recognizes that for a charged particle to maintain its energy while accelerating around the nucleus is indeed a fundamental problem. But it offers a very different solution. According to AND theory, the electron, as it accelerates around the nucleus, is constantly emitting and immediately reabsorbing photons in an incredibly short time, a process known as virtual self-interaction. In this way, the electron maintains perfect equilibrium, and the question of its spiraling into the nucleus never arises. The atom's stability around the nucleus is not an exception to classical physics, but the natural consequence of incorporating new forms of interaction discovered after quantum mechanics had reached its present form. Virtual self-interactions such as those resulting in the electron's stability around the nucleus is not an exception to classical physics, but the natural consequence of incorporating new forms of interaction discovered after quantum mechanics reached its present form. These include the virtual self-interactions of the bound electron as it orbits the nucleus, a process that maintains the electron's energy integrity through rapid cycles of photon emission and absorption. These virtual interactions are directly analogous to the constant exchange of gluons that preserve stability within the atomic nucleus itself. The genesis of the photon. In modern quantum theory and in the Standard Model also, photons are described as excitations of the electromagnetic field, disturbances that arise spontaneously within a universal quantum medium. While mathematically convenient, this picture creates severe conceptual difficulties. Photons are known to be emitted and absorbed at incredible rates, often hundreds of trillions of times per second. To imagine these events as random excitations arising somewhere within a field, triggered from afar and perfectly synchronized to produce photons of the exact energy, frequency, wavelength, and in the quantities required, all within the limited time frame permitted, stretches plausibility. The mechanism lacks verisimilitude. It provides no clear origin, no point of formation, and no means of ensuring the precise correspondence between photon and electron. Augmented Newtonian Dynamics, and theory offers a more direct and physically grounded view. It envisions the photon as being born within the electron itself, in immediate response to changes in the electron's own energy. When an electron needs to shed excess energy, it does so by emitting a photon. When it requires energy, it absorbs one of the requisite magnitude. In either case, the process is internal, local, and instantaneous, not mediated by an external field but governed by the electron's own structure. When the electron needs to release excess energy, it emits a rapid succession of electric pulses, each pulse slightly weaker than the one before. This process results in the polarization of these electrical pulses. The pulses are emitted so quickly, within about 10 to the power of -18 seconds, that they have no time to disperse. The slight difference in their magnitudes establishes a polarity between the first and last pulse, creating a transient electric dipole. This dipole constitutes the photon itself, a compact, stable structure of potential energy held between two opposite poles, which immediately departs the electron at the speed of light. This mechanism confers profound advantages. Because the photon's dipole structure is self-contained and inherently stable, it can maintain its energy indefinitely once formed. It also allows the electron to regulate its energy with exquisite precision, to emit when it must lose energy, to absorb when it must gain it. When the electron releases energy, it emits a rapid succession of electric pulses, each pulse slightly weaker than the one before. These pulses are emitted so quickly, within about 10 to the power of -18 seconds, that they have no time to disperse. The slight difference in their magnitudes establishes a polarity between the first and last pulse, creating a transient electric dipole. This dipole constitutes the photon itself, a compact, stable structure of potential energy held between two opposite poles, which immediately departs the electron at the speed of light. This structure also matches all current observations of the photon. It is massless, electrically neutral, always travels at the speed of light, and preserves its energy intact over unfathomable distances. Unlike the abstract field excitation of quantum theory, the photon in theory is a real, self-sustaining physical entity, the smallest unit of light, formed and emitted directly by the electron in response to changes in its own energy state. In this way, the electron becomes the true architect of light, the source and regulator of every photon that exists. Emission and absorption of light, directional alignment. For us, the inhabitants of Earth, sunlight is a familiar companion. Every day, for hours on end, our planet is bathed in a continuous spectrum of radiation streaming from the sun. Think of what this truly means. For every second that sunlight falls on Earth, countless atoms are being struck by photons, a process that never ceases during daylight. According to Augmented Newtonian Dynamics and theory, atoms absorb and emit energy only at optical frequencies, and for receptive atoms this interaction occurs at astonishing rates, hundreds of trillions of times per second. Imagine electrons within those atoms absorbing and re-emitting photons at that rate continuously throughout the day. In the depths of space, and close to stars, this same process can persist for millions of years. Yet this aspect of photon absorption and emission, its sheer persistence and order, has received surprisingly little attention in physics. Consider what it implies. Electrons are continuously absorbing and re-emitting photons at rates of hundreds of trillions per second, and each of those emissions follows a simple classical rule: the angle of emission is equal to the angle of incidence. For as long as an object is irradiated from a given direction, the electrons of its atoms emit photons in the exact reverse of that direction. The result is the formation of rays of light, vast trains of trillions of photons, each identical to the next, all carrying the same energy, frequency, and wavelength, and all traveling in the same perfectly straight line. Light, in this view, is not a random or statistical phenomenon. It is the direct, continuous outcome of countless ordered emissions and absorptions taking place within matter itself. The coexistence of real and virtual photon processes. If electrons in atoms are continuously absorbing and re-emitting photons of light, one might wonder how they can also remain stable. Would not this constant exchange of energy upset the delicate balance that holds the atom together? In Augmented Newtonian Dynamics and theory, it does not, because the two processes, though related in origin, operate at different frequencies and in entirely different ways. The emission and absorption of real photons occurs directionally, at optical frequencies of about 10 to the power of 14 Hz. These interactions give rise to light as we perceive it, the orderly propagation of energy along straight paths defined by the laws of reflection. By contrast, the virtual photon exchanges that stabilize the atom take place at a much higher frequency, around 10 to the power of 15 Hz, and do so in random directions. Each virtual emission momentarily aligns the surrounding photon ether. Each reabsorption collapses that fleeting alignment and restores the electron's energy. Because these cycles are both extremely rapid and geometrically random, they proceed independently of the slower, directional exchanges that produce light. In this way, the electron performs two complementary functions at once. Through its virtual self-interaction, it maintains internal stability. Through its real photon interaction, it communicates with the external world of radiation. The two rhythms, one inward and random, the other outward and directional, never interfere because they belong to distinct harmonic orders of the same underlying mechanism. Thus, while the atom participates in the luminous exchange that fills the universe with light, it simultaneously preserves its own equilibrium through continuous self-regulation. Matter and radiation are therefore not opposing phenomena, but two expressions of a single universal process, the ceaseless dialogue between the electron and the photon ether. Spin, the dynamic signature of self-regulation. The same process that keeps the electron stable and allows it to emit light also gives rise to one of its most remarkable properties, spin. In conventional quantum mechanics, spin is treated as an intrinsic property, a kind of built-in angular momentum with no actual rotation. It is described mathematically but never visualized physically. The electron simply has spin, without any explanation of how or why. Augmented Newtonian Dynamics and theory restores a physical meaning to this elusive concept. In the and framework, spin arises naturally from the same process of continuous photon emission and reabsorption that maintains the electron's energy integrity. Each act of emission and reabsorption imparts a minute impulse to the electron, a subtle recoil as its energy briefly leaves and returns. Though each impulse is infinitesimal, the sheer rate at which they occur, about 10 to the power of 15 times per second, gives rise to a sustained internal motion. Spin is therefore not an abstract attribute but the dynamic signature of self-regulation, the rhythmic echo of the electron's own photon exchange. Because the electron's emissions occur in random directions, one might expect these impulses to cancel out completely. Yet the process is not entirely without structure. Although the absorptions and emissions take place in random directions, the limited spatial locality of these events, confined to the region immediately surrounding the electron, gives rise to a spin-like dynamic. This persistent, self-referential motion manifests as two complementary states of orientation, corresponding to what are conventionally described as spin-up and spin-down. These are not abstract quantum numbers but real dynamical states emerging from the electron's continuous dialogue with the photon ether. This intrinsic motion defines how electrons share space within an atom and determines the pattern by which they occupy successive energy levels. It also governs the magnetic properties of matter itself. Where quantum mechanics introduces spin as a mathematical correction to fit experimental data, AND theory reveals it as a natural and inevitable consequence of a self-interacting particle maintaining its own energy equilibrium. The Aufbau principle and orbital structure. While Niels Bohr was formulating his theory on the structure of the atom, he correlated data from the hydrogen spectrum with a system of discrete atomic orbitals. In doing so, he proposed three parameters that governed an electron's motion around the nucleus: the atomic number, which determined the nuclear charge and hence the strength of attraction, the atomic mass, and the angular velocity of the orbiting electron. These criteria seemed to describe the hydrogen atom remarkably well, yet they soon proved insufficient. They could not account for more subtle phenomena such as the Zeeman lines, the fine splitting of spectral lines observed when atoms are placed in a magnetic field. Under these conditions, what had appeared as a single spectral line divided into several closely spaced components. The effect implied that something within the atom was responding differently to the magnetic field, that there were internal orientations or motions the Bohr model had not taken into account. The German physicist Wolfgang Pauli examined these discrepancies and concluded that a fourth property was required to describe an electron's orbital state. He called this property spin and showed that it could exist in only two orientations, up or down. The resulting fourfold description worked astonishingly well in explaining atomic spectra and the periodic structure of the elements. There was, however, one unresolved problem. Just as de Broglie could not specify what exactly was waving in his matter waves, Bohr and Pauli could not say what, in physical terms, was actually spinning. Augmented Newtonian Dynamics and theory follows Niels Bohr's essential assumption that the placement and number of orbitals are determined by physical properties of the atom itself. However, where Bohr relied on fixed mathematical postulates, AND theory provides a continuous physical mechanism linking those orbits to the real interactions taking place between the nucleus and its electrons. In this framework, the structure of the atom arises naturally from the balance between the nucleus's energy and the self-regulating behavior of the electrons. Each electron maintains its stability through its rapid cycle of virtual photon emission and absorption, continually adjusting its energy in response to the nuclear field. Stable orbits emerge wherever this process achieves equilibrium, where the electron's photon exchange rate, the local potential around the nucleus, and the electron's own kinetic energy align in perfect balance. Thus, the so-called quantized orbits of Bohr's model are not discrete energy steps imposed by mathematical rules, but natural harmonics of interaction between the electron and the nucleus. Each orbital represents a region where the dynamic exchange of photons sustains a standing equilibrium, allowing the atom to exist in a stable and self-organizing state. Each orbital, once formed, represents a region where the electron's photon exchange is in equilibrium with the nuclear energy field. But the balance within any orbit can only be maintained under very specific conditions. When a second electron enters the same orbital, its own virtual photon cycles must adjust in relation to the first. If their emissions occurred in the same phase, their combined radiation pressure would disturb the delicate stability of the orbit. The two electrons would repel each other energetically even before electrostatic repulsion was considered. However, if their photon exchanges are antiphased, each electron emitting when the other is absorbing, their effects cancel perfectly. This antiphase relationship creates a state of mutual stability and allows only two electrons to share the same orbital. In this way, the Pauli exclusion principle emerges naturally from the physics of photon exchange. The two allowable spin states are not abstract quantum numbers but complementary modes of energy regulation, ensuring that the total photon activity within each orbital remains balanced. Every higher shell represents a new harmonic of this same process, shaped by the increasing nuclear charge and the need to preserve dynamic equilibrium throughout the atom. Emergence of the periodic law. As the nuclear charge increases from one element to the next, the balance between the nucleus and its electrons adjusts accordingly. Each additional proton strengthens the nuclear energy field, pulling the electrons inward and creating new regions of equilibrium where photon emission and absorption can once again stabilize. These regions form the successive shells and subshells of the atom. Each represents a distinct harmonic of the same underlying interaction, a stable resonance between the energy of the nucleus and the self-regulating activity of its electrons. This natural sequence defines what chemists call the periodic law. Instead of being an arbitrary repetition of quantum numbers, the periodicity of the elements reflects the physical harmonics of photon exchange that emerge as the atom grows in complexity. Every row of the periodic table marks the appearance of a new level of stability, born from the dynamic dialogue between nuclear mass and electronic self-regulation. When this delicate balance is disturbed, for example, when an atom is placed in a magnetic field, the geometry of photon exchange shifts slightly. The orientations of the electron's spin states precess in response, producing minute changes in energy. This results in the splitting of spectral lines into closely spaced components, the phenomenon known as the Zeeman effect. Under augmented Newtonian dynamics, this effect is not a mathematical curiosity but direct visual evidence of the mechanism that governs the atom itself. Light, spin, and structure are all facets of one continuous interaction between matter and the photon ether. Formation of the periodic table. Under augmented Newtonian dynamics and theory, The periodic table emerges directly from the stable configurations that electrons can achieve around the nucleus. Each orbit represents a state where the electron's emission and absorption of photons are in perfect balance with the nuclear energy field. As the nuclear charge increases, this equilibrium must be re-established at greater distances and in more complex harmonics, producing successive shells in accordance with the relation 2n², where n is the principal energy level. Each level can accommodate only a specific number of electrons because only those configurations maintain dynamic equilibrium. Beyond that limit, the interaction becomes unstable, and a new orbit forms at a higher harmonic of photon exchange. This pattern, 2, 8, 18, 32, and so on, defines the framework of the periodic table. Within each major shell, smaller patterns of stability appear, corresponding to the S', P', D', and F blocks. These blocks reflect the natural, symmetrical ways in which electrons distribute their photon interactions in three-dimensional space. Unlike the eccentric orbits of quantum mechanics, with their ellipses, ovoids, and dumbbell-shaped probability clouds, the orbits of A and D theory evolve in smooth, harmonic symmetry, governed entirely by energy balance. Each sublevel represents a simple geometric progression of equilibrium, not an abstract probability pattern. The periodic repetition of these blocks arises naturally as each new shell recreates the same hierarchy of stable configurations at a higher energy level. The periodic table therefore reflects a fundamental law of nature, stability through resonance. Gravity, the isotropic residual of virtual photon alignment. If light and atomic stability are governed by photon exchange, it is natural to ask whether the same process might also shape the large-scale behavior of matter. In Augmented Newtonian Dynamics and theory, gravity is understood not as a separate fundamental force, but as the isotropic residue of the same virtual photon interactions that stabilize electrons within atoms. Every electron, as it maintains its energy through constant emission and reabsorption of virtual photons, briefly aligns the surrounding photon ether. Each emission represents a minute ordering of the virtual photons in its vicinity, a temporary directionality within the background field. Although these alignments collapse almost immediately, they leave a fleeting geometric connection that can extend to nearby matter. When two bodies are present, their respective virtual photon alignments tend to coincide along the shortest possible path between them. This shared line of alignment represents the path of least resistance through the photon ether and gives rise to a small but consistent tendency for the two bodies to draw together. Because these emissions occur in random directions and are instantaneous, one-off events, that furthermore are immediately cancelled through reciprocal absorption, their effects almost completely cancel. Each virtual photon emission creates a momentary alignment of the surrounding photon ether, but this alignment collapses the instant the photon is reabsorbed. Because of the dipole nature of the virtual photon ether, dark matter, that instant is enough for the alignment to extend into astronomical distances. Only the tiniest residual geometrical bias remains, yet it is universal and always attractive. The enormous difference in strength between the electromagnetic and gravitational forces arises directly from this geometry. When a real photon is emitted as light, its energy travels in a single, well-defined direction, reinforcing each successive photon in a coherent line of force. By contrast, virtual photon emissions are isotropic and momentary. Their alignments extend briefly in every direction, and their individual effects are dispersed across an entire sphere of possibilities. Only the smallest fraction of this total alignment acts along the line connecting two bodies. The ratio between these two conditions, a directional stream versus an isotropic one-off emission, corresponds closely to the geometric dilution of energy over a spherical surface, yielding a difference in effective strength of roughly 10 to the power of 40 to 1. Gravity is therefore not a continuous flow of energy, but the aggregate effect of countless transient alignments, each representing the shortest line between 2 points in the photon ether. It is the quiet residue of the same process that gives rise to light, a single, isotropic whisper for every shout of electromagnetic radiation. Supergravity, the neutrino regime. In a neutron star, matter reaches densities where the familiar structure of atoms no longer survives. Electrons and protons merge to form neutrons, and the remaining energy of collapse is released in the form of neutrinos, high-energy, one-off emissions produced during the very conversion of matter itself. Each neutrino carries tremendous momentum, enough momentum to give the impression that it possesses mass. In these extreme conditions, neutrinos are produced in unimaginable numbers, and their collective behavior dominates the energy dynamics of the star. Ordinarily, neutrinos pass through matter without interaction, but in the compact interior of a neutron star their sheer abundance creates a new state of equilibrium. The intense outward torrent of neutrinos generates a corresponding inward counterreaction, binding the star through its own energy release. This inward reaction is what gives the neutron star its immense gravitational strength, a form of supergravity born not from geometry alone, but from the density and directionality of neutrino emission. When another star lies nearby, the flood of neutrinos from the neutron star strikes its surface, disrupting nuclei and liberating further neutrinos in return. This reciprocal effect amplifies the alignment of energy flow between the two bodies, drawing them inexorably together. The process continues until the companion star begins to disintegrate, feeding its matter into the gravitational furnace of the neutron star itself. Thus, the gravity of a neutron star is not mysterious, but the natural outcome of energy-seeking equilibrium under extreme conditions. In the neutrino regime, every emission carries the potential to bind. Every burst of radiation strengthens the inward pull. This is supergravity, the stage between ordinary attraction and total confinement, the threshold that leads to the birth of a black hole. Conclusion: the two rhythms of existence. In the universe described by Augmented Newtonian Dynamics, and all matter and energy arise from a single underlying process, the continuous exchange of photons within the cosmic ether. Yet from this one foundation, two distinct forms of order emerge, defining everything that exists. Fermions, the building blocks of matter, electrons, protons, and neutrons, maintain their individuality through self-regulation. Each sustains its energy through a precise rhythm of internal interaction. For the electron, this takes the form of a rapid cycle of photon emission and absorption, a process of self-interaction that continuously restores its energy and maintains its orbital stability. For protons and neutrons, which are composite particles, this self-regulation occurs internally through gluon exchange, the binding process that holds their constituent charges in dynamic equilibrium. Together, these mechanisms form the physical basis of spin, a continuous internal motion arising from the particle's effort to maintain energy balance. When two fermions approach identical states, their rhythmic exchanges interfere destructively. Their wave functions are antisymmetric, cancelling at perfect overlap. Thus, fermions can never share the same state. This is the physical meaning behind the Pauli exclusion principle. Matter acquires structure precisely because self-regulating particles must remain distinct. Bosons, by contrast, are the mediators of connection. Photons, gluons, the W+ and W particles and other carriers of force. Their wave functions are symmetric. When they meet, they reinforce one another, merging into coherent fields of shared vibration. Unlike fermions, they lack the self-correcting feedback of internal interaction, and are therefore free to superpose perfectly, moving in synchrony and amplifying one another's presence. This property allows light to travel, fields to propagate, and energy to link every part of the cosmos. Matter and light. Superposition, then, is not exclusive to one or the other, it is universal. But its outcome depends on the nature of the participant. In fermions, superposition leads to structure through exclusion. In bosons, it leads to coherence through inclusion. The one builds boundaries, the other dissolves them. This is the fundamental duality at the heart of existence. Fermions stay apart, while bosons move together. From that simple principle arises the architecture of the universe itself, the solidity of matter, the fluidity of light, and the ceaseless dialogue between separation and unity that defines the cosmic order. In Augmented Newtonian Dynamics, this principle extends naturally to the realm of hadrons, particles composed of quarks bound through gluon exchange. When three quarks combine, as in protons and neutrons, their spins couple to produce a half-integer total, preserving their fermionic character. But when a quark and an antiquark unite, as in mesons, their spins may cancel or align to form integer values, giving rise to bosonic behavior. Thus, Mesons such as pions and kaons represent the bridge between matter and force, composite systems where the self-regulating rhythms of fermions merge into the shared coherence of bosons.